thank you for the introduction and for folks organizing this conference. It's been a lovely meeting so far. As you heard, I'm William Huggins. I'm here from Google Quantum AI to tell you a little bit about this project, this paper that we called Productionizing Quantum Mass Production, which at least is an attempt to help address this issue of loading classical data into a quantum computer. But before I get into sort of what we did and how well it works or not, I do want to say if reviewer 2 is in the audience, productionizing is in fact a word. It's not even a very modern word, but it's not a very commonly used one. But also, maybe more importantly, I want to say thank you to a number of folks, my co-authors, Tanuj and Nathan, as well as people who are involved in some helpful discussions and contributed some of the ideas I really enjoyed in this paper. And then also, I'm going to show you later on some concrete resource estimates, because part of this project was analyzing these kind of interesting abstract ideas and showing that there's a regime where they might really be useful in practice. And that was made a lot easier by this Qualtran software package for studying fault-tolerant quantum algorithms. And then everything I'm going to talk to you about builds on these earlier works on mass production. And so if you find the rest of the talk interesting, I encourage you to go check out those as well as our paper. And so, yeah, I think it's not a controversial statement for this audience to say that loading classical data onto a quantum computer is expected to be very expensive. And this may be a limiting factor for a lot of the applications that we're interested in, especially perhaps in machine learning, but also in lots of other domains as well. And the notion of loading classical data that I'm going to focus on here is this sometimes referred to as quantum read-only memory, or QROM. And what you should think of is that we have some Boolean function written down maybe on a hard drive on our classical computer. So it's a mapping from n bits to m bits, and it could represent some more structured data, but we can just talk about it in this sense. And what we'd like to do is implement an oracle that loads this thing in superposition onto our quantum computer. For some input register x, whatever's in there, it XORs f of x into this output register. This is the basic kind of object that we're interested in. There are nice constructions for doing this in the quantum circuit model, where we're going to be working for the rest of the talk. And these constructions are nice, but they're also expensive. So if you're just counting the number of Clifford gates to implement a thing like this, you're looking at something like 2 to the n times m, just scaling with the amount of data you have to encode. There are nice tricks for reducing the number of non-Clifford gates that one needs. There's this tunable parameter lambda that lets you use extra space in order to reduce the number of non-Clifford gates that you need up to some factor. We'll come back to this lambda a little bit later, but it's all still very expensive. And so the hope is that we can, in some situations, reduce the cost of doing this. And I'm just going to tell you the punchline before I explain the details, which is that there is a way to implement multiple parallel queries to a QROM like this almost for free. And I'll be a little more precise now. So I'm going to be perhaps too precise, but bear with me. I'm going to walk you through the theorem in our paper that explains what I meant by that last statement. So let's say that we have such a function f. It doesn't matter what it is. This applies in general. And we'd like to implement this O of f. And we also are going to have this lambda parameter that lets us reduce the number of non-Clifford gates that we need. Lambda can be large, but it can't be too large, is what we're saying here. So then we're going to have another parameter, r, which also, it can't be too large. It can't quite be exponential in n, but it can be very large. And so for any r like that, that's a power of 2, what we're going to do is construct a quantum circuit that produces r parallel queries to this QROM. And it's going to have some nice properties. First of all, there's no tricks. It's just made of 1 and 2 qubit Clifford gates and Toffoli gates. And the number of 1 and 2 qubit Clifford gates that you need to implement this thing scales as something that's independent of the other problem parameters times this 2 to the n times m. So that's the cost of roughly of just doing this once. And furthermore, the number of Toffoli gates has a qualitatively similar property. It scales as some constant factor that's hopefully not horrible, and some subleading things times this 2 to the n times lambda inverse. And so what we're saying here is that given these conditions, basically we can implement in an asymptotic sense these R parallel queries sort of for free. This is the notion of free. And at this point in the talk, you probably have two questions. One of them is like, how do you do this? And then the other one, which is also really natural when we present asymptotic results like this, is, okay, well, is this going to be useful in any practical application ever? So we're going to look at those two questions in the rest of the talk. And I'm going to start with how you do it, because I think this is just the neatest part of it. This is drawing on older work, kind of adapted to our context, but it's still, just thinking about it was my favorite part of this project, so I hope you enjoy it also. And the idea is that first we'll need a little bit of notation, but bear with me. So one thing that we're going to think about doing is we're going to fix the first few bits of f. So I'm defining these functions f sub l, and you should think of L as like it's representing the first few bits, the first k bits, say, of our input. And then we're going to evaluate it on another n minus k bits. And we're just going to do that by concatenating them. So we're just fixing the first few bits of f to this L. And then we're going to define these g functions. So g sub 0 is f sub 0. G sub 2 to the k is sort of f sub 2 to the k minus 1. And then the g sub l's in the middle are the XOR of two of these f functions. That's a fine thing that we can do. We can define them this way. And the thing that is nice about these functions is that they give us two equivalent ways of writing down this thing. F basically evaluated on this, L concatenated with Z. One thing that we can do is we can start with G sub 0 and evaluate it on Z, and then XOR that with G sub 1 on Z and G sub 2 all the way up to this L. Or equivalently, we can start with G sub L plus 1, and we can XOR our way up to G sub 2 to the K. So there's two different ways of evaluating F using these Gs. And this is kind of the secret sauce. And I'll explain how it helps us on the next slide here as I walk you through sort of the circuit for producing two of these queries for the price of roughly 1. Before I talk to you about the middle bits, let's just look at the input and output here. There's an ancilla qubit, which doesn't really matter to us right now. We have two inputs, x and y, and I've separated out the first k bits and the remaining bits. And then we have two output registers. And what I'm claiming is that we run this circuit, which I'll explain in a little bit of detail at least. And then when we do that, we've completed the task. We've XORed f of x into one of the output registers and f of y into another. We're going to assume that the inputs are sorted, which we could have done beforehand. So x is less than or equal to y. And that's fine. We can do that without loss of generality because we could just sort beforehand. And so what's happening then in this circuit? Basically, we're using these g's to evaluate the little g functions that I explained on the last slide. And so we're starting with our inputs for x, and we're using this idea of g sub 0, XOR g sub 1, XOR g sub 2. So we're evaluating this f of x by XORing up from g sub 0. And these A's are sort of doing the control flow of our program, which I'm not going to elaborate on in detail here, but they're just either piping the stuff for x or the stuff for y into these g's. And what I claim, and if you're interested in making sure that I'm not lying to you, you can go take a look at our paper, but what I claim is that by the time we've done this, we have in fact completed our task, kind of using the logic of this g sub 0, XOR g sub 1, and so on from the last slide. And furthermore, that the dominant cost of doing all of this is really doing these smaller data lookups. So these things are looking up a smaller function that still outputs m bits, but it only acts on n minus k bits. And if we just count how many there are, there's 2 to the k plus 1, and we can multiply that by the cost of each of them, if maybe just thinking about the Clifford gates for now. And what we find is that the cost is just slightly more than the 2 to the n minus m cost of doing this once. And so this is our sort of 2 for the price of 1 construction. And we can go beyond this inductively. I won't walk you through it in detail, but I just wanted to show you this picture. So imagine that we can do 2 for the price of 1, and we can do 4 for the price of 1, And then the way that we would show that we can do sort of 8 for the price of 1 is we imagine 4 copies of this like original kind of 2 for the price of 1 construction. These are the gray boxes. And the thing that dominates the cost of all of that are these data lookups. But if we lay them out next to each other, we realize that we're just doing 4 of those data lookups in parallel. And so we can use our 4 for the price of 1 construction to do this sort of 8 copy version cheaply as well. And if you track the cost carefully, what you find is that you can in fact prove the result I showed or sort of other variations of it and get this nearly free parallelization. And I realize that I won't be able to tell you all of the things that I really enjoyed about this paper, but I do want to highlight one thing that I think is an important contribution of it, which is that we actually were able to look at how much would this cost to do for some like practical problem sizes that one might imagine implementing eventually on a fault-tolerant quantum computer. And that's what this plot here is showing you. So as a function on the x-axis of the number of input bits, and fixing, say, this number of output bits just to 40, because that's a number that you might use in certain problems, I can show you for different numbers of how many queries I'm doing in parallel, 2, 4, 8, how much better I do than a sort of naive approach where I just do each thing separately as a separate, totally separate data loading circuit. And for the 2-copy version, we get to this nearly a factor of 2 savings. The 4-copy version, you get to this nearly a factor of 4 savings. And asymptotically, if you make all of the numbers really big, you can say that there's a speed up of a factor of 100 or whatever number you'd like. But maybe more importantly, in this kind of regime here where the number of input bits isn't too large, even with this construction that we present, which I hope is not optimized, I think some things about it are, but there's room to do better, you can save some reasonable amount on the cost of doing this data loading. Maybe rather than dwelling on some of the applications here, I just want to make one more point before I close, which is that this result that I've shown you depends on accounting for the costs carefully. And this plot is basically showing you the same thing on the y-axis and the same notation for these colored lines here. But on the x-axis, I'm showing you how much more expensive is a T-gate, a non-Clifford gate, than a 1 or 2 qubit Clifford gate. And so the way that we often think about fault-tolerant quantum algorithms lives infinitely far to the right here, where we only count T-gates, and this protocol gives you no advantage. We explain intuitively why that is in the paper, but in reality, we really expect to live somewhere here, where a T-gate is maybe a little more expensive, but not infinitely so, and you do actually benefit from doing this. And I just wanted to show this because I think it highlights that you could get a qualitatively incorrect conclusion if you aren't thinking carefully about sort of costs in these fault-tolerant quantum algorithms. If folks find this interesting and are wondering where it might be useful in practice, I'd love to chat with you about this slide, which I'm going to zip past, or this slide that analyzes a particular example from chemical simulation to say that there is some regime to benefit. And instead, I'll just emphasize that you can, in fact, speed up data loading in a parallel setting, and you can do it in a practical regime, at least to an extent, and I think there's room to do even better if one really optimizes these constructions. So with that, I'll say thank you, appreciate your attention, and your coming back from lunch.